Welcome to the Team 11 Mars Shelter Design Optimization. The goal of our project is to minimize the total mass of the habitat structure, energy system, and food supply of a Mars base for a crew of astronauts on a 180-day trip. The habitat is needed to protect the astronauts, the energy system is needed to power research as well as the habitat, and the food is required to sustain the astronauts. Here's our system flow diagram. You can see our subsystem inputs, some coupling variables between the subsystems, as well as subsystem outputs, and then finally our system output. Here you can see some parameters for the energy system, as well as food properties for the food supply subsystem. And here are some parameters for the habitat structure subsystem.
Now we will take a look at the system design variables. We start on the left with our local variables within each subsystems. There are 4 for the energy system, 1 for the food supply, and 6 for the habitat structure. There are also 3 inter-subsystem variables. These couple variables link the subsystems together. Now let's dive deeper and look at some of the intermediate variables. These local intermediate variables are used to calculate other variables by using the parameters and equations we defined. The energy system intermediate variables include power contribution from solar and nuclear sources, and power storage capabilities using hydrogen and batteries. The food supply intermediate variables include calories from 4 different food groups. The habitat structure intermediate variables include those that define the geometry of the habitat structure and those that calculate the amount of stress the structure must endure. Beyond the local intermediate variables are system intermediate variables, which are the mass of the 3 subsystems. The energy system mass is the sum of the 4 power systems. The food supply mass is the total mass of all food. And the habitat structure mass includes the mass of the cement wall and the mass of the insulation layer. Now that all variables are defined, let's look at their constraints. Starting again with the local. The energy system constraints define the relationship between power generated and power demand. The food supply constraints include calorie and nutrition requirements. And the habitat structure constraints make sure that the structure satisfies its dimensional, thermal, and structural requirements while providing enough storage space. Our system-level constraints on power demand and food volume are continuous and real, while the number of people is a positive integer. Lastly, our objective function is to minimize the sum of the 3 subsystems' mass.
Our system optimization differs from our subsystem level in its inclusion of 3 coupling variables. Several trade-offs are observed as a result of this coupling. For example, increasing the number of astronauts required for energy maintenance greatly affects habitat size and food required. Reducing thermal insulation mass constraints increases power requirement, and increasing meal variety constraints increases volume required to store food in the habitat. Moving on to our mathematical modeling section, our approach consists of an analytical modeling method with closed-form equations and both linear and nonlinear constraints. Some assumptions we made for this system include that the habitat aggregate can be sourced on Mars, that power systems require human maintenance as opposed to employing automated maintenance, and that the number of astronauts required for colonization is entirely determined by the size of the energy system. These assumptions, as well as many others, are oversimplifications that affect the accuracy of our model but reduce its complexity to a manageable level. This next slide dives into the specific modeling steps we followed. Our strategy involved using an individual disciplinary feasible or IDF formulation. This method is computationally inexpensive compared to other formulations and is compatible with both weak and strong subsystem coupling. Following this formulation, we decoupled our subsystems using individual auxiliary coupling variables with equality constraints. Side constraints were added for both feasibility and to reduce complexity in the genetic algorithm populations. This system could then be solved by iterating through subsystem and then system-level optimization. Here's a quick look at a simplified system flow diagram before incorporating IDF decoupling. As you can see, variables are passed down between the subsystems in multiple feedback loops. This next slide shows our IDF decoupled system flow diagram. With this method, subsystems can be solved independently and equality of coupling and auxiliary variables need only be satisfied at convergence.
Moving on to the optimization method and results. When selecting a solver for the system-wide optimization, it was required to use a genetic algorithm solver due to distinct subsystem properties, including discrete variables in the food system and nonlinear constraints in the habitat system. Previous subsystem codes were adapted to work with MATLAB's GA function. Looking at the optimization results, we used 5 separate runs to assess result variability. Due to the stochastic nature of the GA function, different outcomes were created despite identical parameters. System design variables include the number of astronauts, heat loss, and food volume, with the primary output being the total system mass. As you can see, the results did not vary much between runs. In order to understand how the constraints and parameters affect the overall system optimization, key constraints and parameters were chosen for sensitivity analysis. Sensitivity analysis is performed by perturbing the constraints and parameters by 10% in the positive and negative direction, and solving the full system using the new parameter or constraint. High-impact variables were selected for analysis, including key constraints such as breakfast distribution, heat loss, von Mises stresses, and key parameters such as the number of days, insolation R value, and power demand. Only 3 parameters and constraints were chosen due to the high amount of constraints and parameters we have in the long runtime of our model. Looking at the sensitivity analysis results, we can see that the food system had minimal impact on the overall system mass, and therefore its constraints and parameters were less sensitive. As expected, the heat loss showed the highest sensitivity coefficient, with small changes producing large mass variations. The insolation R value had the greatest parameter impact, negatively correlated to total mass.
Moving on to a discussion and interpretation of the results from our optimization. For a reality check on the full subsystem, on average, the total mass of our system was around 15 to 20 tons, which is well within the current rocket payload capabilities. Think of the Starship payload to Mars, which was about 100 tons. However, our system optimization doesn't include other vital subsystems. Think of wastewater treatment, water supply, agriculture, or electronics that would certainly drive up the weight and absorb some of that difference between the 15 to 20 tons that we calculated and the Starship payload that was referenced. Now, for the energy system, our prediction that solar will outperform nuclear within a given band of latitude was agreed with by recent papers that have been released. For these papers, their solar power payload estimate did differ from ours by about 30%. This could be attributable to a difference in the model complexity. For the food system, the results of our optimization indicate that for both mass and volume, we're a bit lower than what is reported per astronaut per day from NASA currently. This could be attributable to the fact that NASA allows their astronauts a lot more autonomy in their food selection than our model does. In addition, the packing density that we assumed for this food of optimal packing density may not be reflective of reality, and more food storage may be needed in a real Mars habitat. Our habitat subsystem allocated a living space of around 40 meters squared per astronaut, which matches really well to what NASA is currently simulating in the Chapia House Martian habitat experiment. However, the Chapia House is a rectangular shape, so we know that our subsystem modeling of a spherical cap may underestimate the actual heat loss that you might see due to a difference in surface area to volume ratio in a rectangular habitat. Overall, our model, while highly hypothetical, does remain pretty consistent with published Mars habitat predictions.
So, comparing the subsystems to the system as a whole, we initially started with the number of astronauts as a parameter set to 4. This simplified the optimization of the entire system and allowed it to converge more easily. Given our power maintenance consideration, after running, the optimization converged to 5 astronauts, meaning increases in food volume and the habitat size. More realistically, for a future manned mission, these tasks could be automated to compensate and require less astronauts and thus less total system mass. Overall, the number of astronauts produced the most significant effects on the food and habitat subsystems and consequently overall system weight. Our other coupling variables of food volume and habitat heat loss had much more negligible effects on the system. Intuitively, we can see how these limited effects did not cause much of a change in the final results of our system when compared to those from the interim. To summarize, our model has predicted an optimum total system weight of about 15,000 kilograms across our 3 subsystems. Specifically, around 40% of this weight will come from the habitat structure and its contents, while the other 60% comes from the machinery for solar power and battery storage. Of course, we acknowledge all the assumptions that we made along the way. Looking towards the future, optimizing a Mars base is critical for successful colonization. Our work presents a simplified model, but real mission planning will need to include more subsystems, newer technologies like micronuclear or advanced solar cells, and consider a broader range of factors like radiation, astronaut psychology, and comprehensive resource demands. Future models should also consider the practical constraints, like food preferences or packaging efficiency, to better reflect all the challenges of living on Mars.